Let's talk about the action potential. How do we know what a nerve impulse is and how it is created? Scientists K.S. Cole and J.J. Curtis studied the giant squid axon. They placed electrodes inside the nerve of the squid. Here we see giant squid axons, and they are much bigger than humans' axons. Humans' axons are microscopic. Resting membrane potential, so inside the axon, it is negative 70 millivolts when the neuron is not active. An unstimulated axon is negative on the inside in respect to the outside. An action potential is when there's electrical activity inside the axon. It's when the axon becomes excited and it increases to positive 40 millivolts. Every time the axon is stimulated, there's a change in charge across the membrane. The entire membrane, however, is not stimulated at the same time. We can see right in the middle, we have an action potential where it's positive on the inside. It's moving down the axon. So to become positive here and keep going until it has come to the end of the axon. This action potential can also be called a moving wave of depolarization, propagation of the action potential, or we can say the electrical signal is traveling down the neuron. The charge difference in a resting neuron is due to positive ions. There are more sodium ions, Na positive, outside than potassium ions, K positive, inside the neuron. This separation of charge means that the neuron is polarized. So here we see a neuron, and part of the axon is right here. So here's part of the axon. We can see it's negative on the inside, positive on the outside. On the next slide, we're going to look at just one side of the axon. So right here, this membrane is here. So we have a phospholipid bilayer with a number of membrane proteins inside of it. Outside, we see we have much more sodium than potassium on the inside. Also on the inside are some negatively charged proteins. The first step when an action potential hits is that the sodium channels open and allow sodium to diffuse in. So now it has become positive 40 millivolts. Now, because the sodium and potassium are like charges, potassium is going to be repelled and it will move out. So it moves through potassium channels out. Now the sodium is in, potassium is out, but we need to get it back to polarize. So that's the job of this third type of membrane protein called a sodium-potassium pump. Because it's a pump, it requires ATP to move 3 sodiums out for every 2 potassiums in. It keeps doing this until the neuron has become repolarized, or negative 70 millivolts on the inside. The sodium-potassium pump actively takes 3 sodiums out and brings 2 potassiums in by using ATP. This means there are more positive charges found on the outside than on the inside, resulting in negative 70 millivolts inside the axon. When a neuron is excited, an action potential is generated. During this time, the sodium-potassium pump is turned off. Let's look at this in detail. At negative 70, we have resting potential, or we say it is polarized. At the top of the graph, we say it has an action potential, or it is depolarized. Here where it dips underneath negative 70, it is extra polarized, or we call it hyperpolarized. And then back here, it is back at resting potential, or repolarized. So the ion that is rushing in to cause depolarization is sodium. To become repolarized, potassium rushes out, followed quickly by the sodium-potassium pump, moving 3 sodiums out and 2 potassiums in. Let's draw one more item on our graph. At negative 55 millivolts, we have threshold. Threshold is the minimum amount of stimulus required to cause an action potential. If there's a very small stimulus and it doesn't reach threshold, then there is no information traveling down that neuron. It does not stimulate it. While a neuron is depolarized to repolarized, another action potential cannot hit the same part of the axon because it's already depolarized. So the refractory period is the time for a neuron to recover before another action potential can occur. Threshold level is the minimum level of stimulus required to produce a response, usually negative 55 millivolts. If a stimulus doesn't reach this, then it does not cause depolarization. The all or none response states that neurons either reach threshold and fire or they don't. The intensity, which means the maximum depolarization, and the speed, so the time it takes to recover, of nerve transmission remain the same every time a neuron fires. What can change is the firing frequency can speed up. So let's take a look at that. Here we have slow firing frequency, and here we have fast firing frequency, one right after another. So the faster one would be due to a greater stimulus. Does this follow the all or none rule? We have a number of stimuli that did not reach threshold and it did not fire. Then we have one that reached threshold and it fired. So yes, it does follow the all or none rule because it does not fire until the stimulus reaches threshold. Does this follow the all or none rule? Remember, we said that the neurons always depolarize to the same intensity and take the same amount of time. So this one did not reach the same intensity, so no, it does not follow the all or none rule because it does not depolarize to the same voltage. Let's take a look at the second one. It doesn't take as long as the third one, so it also does not follow the all or none rule because it takes less time. Let's take a look at one more. Here we have a short stimulus, didn't reach threshold. Here we have inhibitory postsynaptic potential, again doesn't reach threshold. We have two excitatory stimuli resulting in threshold, and then it fires. So it does follow the all or none response because it does not fire until the stimulus reaches threshold. How does our brain differentiate between hot and really hot if all action potentials have the same intensity and speed? One is the number of neurons that are excited. Hot would be fewer neurons. Really hot, more or many neurons would be stimulated, which means a lot of information is traveling to the brain about the painful stimulus. The other change could be the firing frequency. Higher frequency means there is more stimulus. Let's label this part of a neuron. We have part of an axon here. Here it's positive on the inside, which we said is depolarized. Notice the direction of nerve impulse is traveling in this direction. So this, number one, is behind the nerve impulse, so it is repolarized. 3 is in front of it. The point of depolarization hasn't hit number 3 yet, so it is still polarized. Let's look at this neuron. Here we have polarized, depolarized, and right behind it, repolarized. On this example, we see that we have a myelin sheath on an axon, and the only point of depolarization is at the nodes of Ranvier. So we have one here, and then it zooms along, speeds up within the myelin sheath, depolarizes here, again speeds up, and then depolarizes only at the node of Ranvier. Inhibitory drugs will lower resting potential, making it harder to generate an action potential. Alcohol is an example of this. Here's our example of alcohol decreasing the resting potential to negative 90 millivolts. So if a stimulus usually to reach threshold was 15 millivolts, then under the influence of alcohol, to reach threshold, a stimulus of 35 millivolts would be required. So a person under the influence of alcohol would not respond to the same stimulus as a person who was not drinking alcohol would.